Hello everyone. It's been a while since we've done an exam paper, and I know that lots of you have found them useful, so I thought we'd return to it. Hello everyone. I know it's been a while since we've done an exam paper, and I know that lots of you found them really useful, so I thought it was important that I go back and I make sure that we slowly get them all done. Hopefully you can understand that it's been quite a chaotic time as a teacher, but I hope you find this useful. So today we're going to be looking at the 2018 Chemistry Paper 1 of the Combined Science AQA exam. I think it's really useful if you wanted to either do it beforehand or follow along with me. In the description is a link to the AQA website, and you can download the paper, you can print it out, and just have a generally good time, because there's nothing anyone likes more than exams. So let's get into it. Okay, so question 1. This question is about structure and bonding. Figure 1 shows part of the structure of calcium oxide, CaO. What type of bonding is present in calcium oxide? Tick one box. Okay, so first thing to note is calcium is a metal, and oxygen, or the oxide part of it, is a non-metal. Okay, whenever we have interactions between metals and non-metals, we get this particular type of bonding, and also these charges giving it away. Okay, these are charged particles, and this interaction between a metal and a non-metal with charged particles is called ionic bonding, because these charged versions of the atom are called ions. So when these ions oppositely charged stick together, we call that an ionic bond. They're held together by electrostatic attractions. I know I've gone into a little bit more detail than just ticking ionic, but it's nice to make sure we're a little bit familiar with the background. Figure 2 shows a particle of methane. There it is. What type of particle is present in figure 2? So we've just said that an ion is kind of a charged, I'm going to put in inverted commas atom, because it's not an atom anymore, but it's kind of a charged version of it. A lattice, well, that's actually what that is. It's the kind of alternating positive and negative ions. A polymer, if you think about the word poly means many. Like a polygon is a shape with many sides. So a polymer is when you have many molecules linked together. So something like a plastic or something like that. A molecule, okay, is covalently bonded atoms. Okay, it's like a group of covalently bonded atoms. So here you can see methane. We've got carbon and hydrogen, and they're covalently bonded, and that means that this is a molecule. Okay. Figure 3 shows the structure of C60. Complete the sentence, choose the answer from the box, and we've got a choice of diatomic, giant ionic, fullerene, or giant metallic. So diatomic, if you think about the word di means two. Okay, yeah, like duo and stuff like that. Di means two. Clearly we've got more than two atoms here. Ionic, remember we said that's got to involve charges. Nothing here is charged, so it can't be that one. Giant metallic, it's not no metals there, is there? So it must be a fullerene. Okay, it's actually named after an architect called Buckminster Fuller, and he used to make these weird dome things, and they look a bit like that, so that's why they called them fullerenes. There you go. Fun fact of the day. So figure 4 shows the structure of graphite. What type of bond is labelled A in figure 4? Well, graphite is a form of carbon, and carbon is a non-metal. Can't spell today. And the bonding between non-metals is covalent. So whenever I have any bonding between non-metals, that is a covalent bond. You can get a double covalent bond, but that's not actually a type of bonding. Ionic, we've said, is stuff to do with charges, and metallic has got to involve metals. In graphite, each carbon atom forms bonds with other carbon atoms shown in figure 4. How many electrons does one carbon atom use to form one bond? Okay, so hopefully you are familiar with the fact that carbon, if I look on the periodic table, okay, these vertical columns in the periodic table are called groups. And the interesting thing about groups is they tell you how many electrons are in the what we call the outer shell. So here for carbon, okay, it's in group 4, so that must mean it has 4 electrons in the outer shell. Okay, so if I have a look at carbon, 1, 2, 3, 4, this is the outer shell electrons only. Now, I always like to think about electrons as them being lonely, right? They want to pair up. They want to have a bit of, they want to go on a date with another electron. And you can see here that each one of these 4 are kind of lonely. All right, so this one can form a bond with something else. This one can form a bond with something else. This one can form a bond with something else. This one can form a bond with something else. So I can actually make 4 bonds here, 4 covalent bonds. You can get double bonds when they all kind of gang up, but you can see here that because if I focus on this carbon here, it's formed to at least 3. So we've got 1, 2, 3 bonds. So that means that each carbon atom, each one bond in that atom is going to come from one from each carbon. That was the world's best explanation. Let me explain. So if I have one carbon here and the other carbon here where it's going to bond with, each one is contributing 1 electron. So that was a long-winded answer to basically say each electron in the carbon atom, okay, gives it a bond. So one carbon atom uses 1 electron to form 1 bond in graphite. An electric current is passed through copper. Figure 5 shows the apparatus used. You've got this DC power supply, battery basically, a filament bulb which lights up, and that tells you that that the circuit is going, and you've got this copper between some electrodes. Complete the sentence. Choose the answer from the box. So if I've got gas, liquid, solid, or solution. Figure 5 shows that copper conducts electricity as a. That's clearly, you can see here. If it was a gas, you wouldn't have a lump of it. If it was liquid, you'd see it as a liquid, right? So it can't be either of those two. It can't be dissolved, so it must be a solid. Okay. 1.7. Choose a sentence from the box. I'll choose the answer from the box even. Copper conducts electricity because of the movement of delocalized something. Okay. What all electricity is, okay, is the movement of charged particles. Now, electricity is super complicated. I think it's one of the worst understood topics at GCSE. I often have said before that I don't think I truly understood electricity until I started being a teacher, right? I think I could explain stuff, but I never really understood what was really going on. Now, copper is a metal, and metals undergo metallic bonding. And in there, we have these positive ions. There they are. And we have these little delocalized electrons. Okay. Now, if you, they're kind of free to move. Now, my way of thinking about this is, if you think about those outer electrons, metals lose them, right, to make a full outer shell. And I like to think about it as that one extra annoying friend that you have in a group. If you don't know what friend in the group, in your friendship group, is the annoying one, it's you. No, it's a joke. I'm joking. Everyone loves each other. And if you told that person just to go away, right, they'd float about, right? So I've got this group of people. That annoying friend has now walked off, and they might poke their head in and go, "Oh, hello, can I be your friend today?" No, and they'll wander off to the next group and they'll go, "Oh, can I be your friend today?" And they'll go, "No," and then you go here, and they kind of can move about all over the place, trying to be everyone's friend, right? We all know one. Now, if I suddenly put this into an electrical circuit and I whacked a very big positive side on this side and a negative side on this side, remember electrons are negatively charged. Okay, so that means that negatives are attracted to positive. So these negative electrons, which delocalized electrons, which can suddenly move about, will go whoop all the way over here, and they'll all swarm down this way, and that is a movement of charged particles, and therefore will conduct electricity. So the thing which is moving and conducting the charge is these delocalized electrons. Okay, so I know that was a big roundabout explanation, but I've basically explained electricity a little bit there in conduction and metals. Okay, figure 6 shows the apparatus used to investigate the effect of electricity on sodium chloride. Complete the sentence. Okay, and you can see here we've got a similar setup, but instead of a metal copper rod, we've got it dunked in a sodium chloride solution. Now, the key word here is solution, right? That gives it away that it's dissolved. Yeah, molten is when things have been melted, and gaseous means it's a gas. So we can see here that because it lights up, it conducts electricity, and it's in a solution, so that means that is when dissolved. 1.9, sodium chloride is made up of ions. Figure 7 shows the apparatus used to investigate the effect of electricity on solid sodium chloride and molten sodium chloride. You've got this DC power supply. You can see that the bulb does not light up now. So that means that this, because it does not light up, that means that this circuit doesn't work. Whereas here it lights up, so that means it does work. Okay. So let's have a look at those results. I mean, look, I've jumped the gun. Look, I've been a moron, really. It's already explained it there for us, which is why I should always read the question first. But I suppose going along and making notes isn't the most unuseful. Draw a line from on each statement for the reason. So, sodium chloride is an ionic substance. Now, remember we said that all electricity is charged particles that can move. Okay. Now, in a solid, these are going to be locked in place. Okay. If you think, remember, in a solid, the particles stay close together and they just vibrate, but they don't move over one another. When I melt it, they can now move past one another. Right? They can be mobile all over the place, and that means that they can now move and conduct electricity. So solid sodium chloride does not conduct electricity because the ions are fixed in place. Okay. Whereas so solid sodium chloride does not conduct electricity because the ions are fixed in place, whereas in molten sodium chloride the ions are mobile. Okay, smashed it. Okay, this question is about the halogens. What group in the periodic table are called the halogens? Okay, so first of all, if you're ever stuck, right, think about it. It just tells you this is one where you can use the question against itself. It says that this question is about the halogens, and imagine in the exam you're really not sure. Well, it then goes on to talk about fluorine, and it then goes on to talk about chlorine. So the first thing you can do is you can look at the periodic table and you can go, fluorine, chlorine, group 7. Okay, I don't know, where did I put my previous one? I've managed to multiply periodic tables. There you go. Just always, I'm a science teacher, I always just have them lying about. It's what I wallpaper my house with. So you can see here, it's in group 7. Okay, so a fluorine atom has 7 electrons in the outer shell. Remember, we said that that group number tells you how many electrons in the outer shell, so that's another clue. Figure 8 shows the part of a dot and cross diagram to represent a molecule of fluorine F2. Complete the dot and cross diagram. You should only show the electrons in outer shells. Well, we've been told there's 7 in the outer shell. Now, I always like to think about electrons on shells as like there's 4 double seats on a bus. Right? Imagine you're getting on a bus and there's 4 double seats. The first person sits wherever they like. All right. Now, if the second person to get on that bus, even before coronavirus and social distancing, if that second person got on the bus and sat next to you and then you didn't know them, you'd find that a bit odd. All right. You would sit away from them. Okay. Third person comes on the bus. Off they go somewhere else. Fourth person, the 4th double seat. Now, when the 5th person gets on the bus, it's socially acceptable to sit next to someone. Alright? So the 5th person, don't obey all social distancing rules, but the 5th person, okay, who gets on the bus, will then sit next to someone. Okay? So the 6th person who gets on the bus can sit next to someone else, and the 7th. Okay? So the best way to draw electron structure, especially going on to look at bonding, is to really think about spreading them out. So you do these 4 points, you know, like 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock, and then you start to double up. So let's use that idea for fluorine. Well, we've said that one fluorine atom will do this, so let's complete that. Okay. So the interesting thing comes here, right? Okay, because I've got one lonely one for fluorine. So what happens is if I have another fluorine, those 2 lonely electrons are like, oh, we're both lonely, why don't we hang out together and then we won't be so lonely. Okay, they're going to form a support bubble. So the one lonely one from this fluorine will go in the middle, and the one lonely one from this fluorine will go in the middle. And you get this kind of overlap where they both hang out together as a pair. And remember that these, it's like a Venn diagram, the bit in the middle, it counts for both. Okay, so if I add up how many electrons I've got, 1, 2, 3, 4, 5, 6, 7, 8. So this fluorine's got a full outer shell, which is happy. 1, 2, 3, 4, 5, 6, 7, 8. Another 8, another full outer shell, everyone's happy. Chlorine reacts with potassium bromide solution. Complete the word equation. So this is what we call a displacement reaction. Okay, if you've ever seen Indiana Jones, okay, you know the bit where he gets to the temple and he's got that gold statue and he's got the bag of sand and he wants to nick the statue. So he takes the statue, he takes the bag of sand and he kind of goes, oh, and steals the statue. That's what's going on here. Chlorine is more reactive than bromine. So it's there, chlorine's there, and it sneaks in the place of the bromine and it swaps over. So I get potassium, not bromide this time, but chloride plus bromine. So I have switched them over. Okay, and I've just said that this is called a displacement reaction. This is when a more reactive substance displaces, or replaces I suppose, a less reactive substance in a compound. Okay, right. Answer 2, okay, or question, answer 2. Question 2.5, complete the sentence, choose the answer from the box. So chlorine is more reactive than bromine. This is because chlorine gains what more easily? So we've just said here that to react, that we've got this one lonely electron. So there's 2 ways that I can kind of make it happy. Okay, atoms don't have feelings, but we'll just pretend they do. We can either share, and then that electron is no longer lonely, or I can gain one. I can find one about. Okay. Remember from last time, here with the metals, okay, I said we've got those lonely electrons wandering about trying to look for a group of friends. Well, suddenly I've got an opening in this friendship group. It can gain their electron. So that's how non-metals react, as they gain electrons. So if it's more reactive, that means it's going to gain an electron more easily. Okay, it means it can more rapidly take that electron in. How does the size of a chlorine atom compare with the size of the bromine atom? Okay. This is where we're now going to think about the rows of the periodic table. The rows of the periodic table are called periods. That's why it's called the periodic table. Okay, and what those periods tell you is the number of shells. Okay, so they tell you how many rings, how many energy levels, circles of the electron, of the atom there are. So if I look at chlorine, chlorine is in the third period. Don't forget hydrogen and helium is a period, so it's in period 3. So chlorine has got 3 periods, 3 energy levels, 3 numbers of shells. So 1, 2, 3. Bromine, 1, 2, 3, 4. So bromine, 1, 2, 3, 4, right? So that means that if I compared them, chlorine is smaller than a bromine atom. Look at that. He's written over the answer. Shocking. Can't get the staff nowadays. Okay, give a reason for your answer to question 2.6. So what we've just said there, okay, is because it's got that one fewer. Can't speak today. One fewer period. Okay, sorry, one fewer energy levels. Okay, or one less energy level. All right. So chlorine has 3 shells. Okay, which is fewer than bromine's 4 shells. There you go. Fluorine reacts with chlorine to produce ClF3. Balance the chemical equation for this reaction. Okay, so to balance it, if I write that equation down, you can see I've got Cl2 plus some amount of F2, I'm not sure about this, goes to 2ClF3. Now, because I quite like Fallout, I bought loads of bottle caps and used them to help balance equations. So you can see there that I've got a Cl2, okay, there it is. I've got some amount of F2, so I'm just going to leave that for a minute. And then I've got 2 ClF3. Now, as the little number is to do with the F's, that means that the previous atom, which is the F's, has got 3 of them, but it means that there's only 1 chlorine. Okay, so I've got 1 to go with that lot, and 1 to go with that lot. So the question now is, how many F2s do I need to balance the equation? Well, look, if I count the number of Cl's, I've got 1, 2 on this side, and I've got 1, 2 on this side. If I look at the fluorines, I've got 1, 2, 3, 4, 5, 6. So I need to have 6 fluorines on this side. I get told they come in pairs. So let's think about this. Well, 1 pair would give us 2. Still not enough. 2 pairs would give us 4. Still not enough. 3 pairs would, however, would give us 6. And that's how we balance it. The key thing to balancing equations is I need to have the same amount of atoms on the left as I do on the right. Okay, I can't make new atoms. The whole idea is that when these react, they can rearrange and make the same thing. Okay, so yeah, look, same thing. So you can see here that they must therefore be 3 F2s. Okay, explain why fluorine is a gas at room temperature. Right, first meaty question. So, you need to use these following words in your answer. So it's a really good idea that we can use this almost like a tick list. Okay, so fluorine, right, and we've just done this, look. Here, fluorine is a covalent molecule, right? The bonds in it are covalent, so it happily exists as this F2 lump, okay, like this. But the issue we've got is, whilst this bond here is really strong, yeah, if I compare two different ones together, the bond between them is really weak. Okay, so whilst the covalent bond is really strong, the bond between any two covalent molecules is actually quite weak. Then we call them weak intermolecular forces. Now, to melt something or to boil something, we need to break them apart. So if those intermolecular forces are really weak, then that means it's going to have a really low boiling point, and it will be a gas. So whenever I answer any kind of longer written question like this, I really want to use as many key terms as I can and make it really telegraphed and sound fancy to the examiner so they know what I'm talking about. So fluorine is a covalent molecule. Now I'm going to say simple molecule. Okay, simple because it's not giant. Yeah, it doesn't go on forever like graphite. Okay. This means that although the covalent bond is strong, there are weak intermolecular forces between molecules. So let's keep the tally so far. We've used molecules, we've used weak, we've used forces. So this is where people then probably are losing that third mark, is because I reckon a lot of people maybe get these 2 marks. Third mark is then think about, why does that mean it's got a low boiling point? Okay. Now, don't be afraid to leave a gap. Don't be afraid to make it super clear. You don't need to have this big wodge of text. As these weak forces require little energy to break, fluorine has a low boiling point and is a gas. Okay, so I've used all those keywords. I've followed through in a logical fashion. Often science answers start with a sentence and then it's this means, this means, this means, this means. You don't need to be fancy, you don't need to have all this guff like in English or something where you have to do all of your peels and petals and all that malarkey, right? Just say a sentence and explain stuff. Right? Easier said than done, I know, but you don't need to worry about if your answer sounds boring. Okay, this question is about acids and bases. Which ion is found in all acids? If I write out some acids, hydrochloric acid is HCl, nitric acid is HNO3, sulfuric acid is H2SO4. The thing here you can see that they've got in common is this H. And that's what makes an acid, is that H, when it dissolves, okay, that H breaks off as H+, and that is the ion which is found in all acids. Zinc nitrate can be produced by reacting an acid and a metal oxide. Name the acid and the metal oxide used to produce zinc nitrate. Okay, so let's think about this. We've got an acid and a metal oxide. So if I've got a metal oxide, that means that this word must end with oxide. Okay? If I had a metal carbonate, that word would be carbonate. I've got to make a zinc nitrate. So whenever I'm making a salt, okay, the first name of the salt comes from the metal that was used. So if I'm going to make zinc nitrate, that must mean I need zinc something, or we've got a metal oxide, so it's zinc oxide. If I'm now thinking about the acid, well, I've got this nitrate. Okay, that nitrate must come from the name of the acid. And I just listed some acid up here. These are the three you probably need to be familiar with: hydrochloric acid, sulfuric acid, and nitric acid. And nitric acid is responsible for making nitrates. So the acid which is going to be used is nitric acid. Okay, this nitric acid gives us a nitrate. Sulfuric acid gives us a sulfate. I suppose I have to use the F. And this gives us a chloride. Okay. In an equation, zinc nitrate is written as Zn brackets NO3 brackets 2 AQ. What does the AQ mean? Okay, right. AQ, these things at the end are called state symbols. Okay, they're called state symbols. And they tell you about how you would find this chemical if you were doing the reaction for yourself. There are four possible ones. There's S, okay, which is solid. There is L, which is liquid. And there is G, which is gas. And then finally AQ, which our question's about. AQ stands for aqueous solution. Okay, think of aqua. Aqueous solution means dissolved in water. Okay, it's dissolved in water. That's where the aqueous comes from. The pH of a solution is 8. Some hydrochloric acid is added to the solution, suggests the pH of a solution after mixing. So the pH scale goes from 0 to 14, roughly. 7 is in the middle. Okay, 7 here is referred to as neutral. And anything to the right, okay, is an alkali. And anything to the left is an acid. So acids make the number lower. So if my pH solution is 8 and I add some acid, it's going to go towards the acid way. Okay. Now hydrochloric acid is pretty strong, so the mark actually comes for saying anything that is between this 0 and 8. You actually get the answer for mark for any of them. So I'm going to pick a number. Let's go with 5. Okay. Table 2 shows the solubility of 3 solids in water at room temperature. We've got phosphorus oxide, silicon dioxide, and sodium hydroxide. The teacher labelled these 3 solids A, B, and C. She gave the student the information shown in Table 3. Describe a method that can be used to identify each of the 3 solids A, B, C. You must use an indicator in the method. Blah, 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 blah. Okay, so we need to indicate we need to find out what each chemical is. So we've got to get our kind of investigation hat on. First thing to say, okay, is that if I've got the mass of the solid dissolved in 100 grams of water is 0, then that means that it's going to be the solid which does not dissolve. So C, we know, is going to be silicon dioxide. Okay. Okay. So we now need to work out which one's phosphorus oxide and which one's sodium hydroxide. Now they both dissolve in water. All right. So what we could do is we could dissolve them in water, and then we're told that one of them goes to pH 14 and one of them goes to pH 2. Sorry. So one of them makes an acid and one of them makes an alkali. Now, even if you didn't know this and you were stuck a little bit, hydroxide is the big thing which tends to be alkalis. Okay, so they are alkalis. So sodium hydroxide, because it's a hydroxide, is an alkali. So if I did that test, I would expect to have a high pH. So we know that A must be the sodium hydroxide. Okay, the one which goes acidic is going to therefore be the phosphorus oxide. Okay. So we've just kind of established which one's which. Whenever you're doing like a method or something like that, there's nothing to stop you just doing a numbered list, alright? Don't need to be fancy here. So the first thing that we did, okay, is we added them all into water, okay? So dissolve A, B and C in water, okay? Now question part 2 says, actually a subsection to point 1 is the one sorry, as C does not dissolve, okay, it must be silicon dioxide. Okay, so we've established that that must be that. Okay. Step 2 is add universal indicator to the solutions of A and B. Okay, so solution A will turn purple / blue, indicating it's an alkali. And that therefore means that it must be sodium hydroxide. So it is sodium hydroxide. Okay, and the last point is that solution B will turn red / orange. It's just going to be red, isn't it? Will turn red, indicating it is an acid and therefore B is potassium, oh not potassium, phosphorus oxide. Okay. Right, question 4 is about the elements in group 2 of the periodic table. It shows the positions of them. Okay. Remember what we said earlier, the groups, okay, are the columns. So the groups are the columns, the vertical bits. So group 2 is going to be 1, 2. So it's going to be element B. Group 2 metal carbonates break down when heated to produce a metal oxide and a gas. Name the two products when calcium carbonate is heated. So we've been given this formula. Okay, so if I've got metal carbonate, right, calcium carbonate is going to go to a metal oxide. It must go to calcium oxide. I've got carbonate, right? Now carbonate, you might know, is CO3. So if I've now only got the oxygen, I've got some form of carbon something, and we get told it's a gas. So there's pretty much only one gas in science that we, in general, that we talk about, which is a gas involving carbon. So it must be, and it is in fact, carbon dioxide. Oh yeah, it's even given there, look. Mr. Pashler's a moron. So the CO3, one of those oxygens is going to go here, so I'm going to end up with CaO, and the rest of them must be here in the gas, CO2. What type of reaction happens when a compound breaks down? Okay, this is where we can really use our words. Okay, composition. If you think about composer, yeah, decompose means to make, right? So if I had decompose, that means it demake or unmake, right? So that's going to be breaking down. So it's a decomposition reaction, means to unmake or break down. The metal carbonate takes in energy from the surroundings to break down. What type of reaction takes in energy from the surroundings? So this is really hinting at, or this is really getting at, these two key science words. We've got exothermic and endothermic. Thermic means energy or heat. And let's now look at the start of the words. If I've got exo, right, that looks like the word exit. So that means to give out energy to the surroundings. And endo looks a little bit like enter. So that means take in energy from the surroundings. So we've been told this reaction takes in energy from the surroundings, so it must be endothermic. Figure 10 shows the volume of gas produced when a group 2 metal carbonate is heated. Okay. A student collected 5.2 decimeters cubed of gas. What mass of metal 2 carbonate is heated? Right. So, whenever we're using a graph, okay, we want to make sure that we're really just following things really neatly. And in fact, I haven't got a ruler to hand, but I have got a block of wood. Don't know why. As you do. So it collected 5.2 decimeters cubed of gas. So I'm going to look up this way. Now, if you have a look, each kind of 5 by 5 box here goes up by 2, right? So I've got 5 little squares. Equals 2. So that means that each little square, so one little square, is going to equal 0.4. So if I've got 5.2, it's going to be 4, 4.4, 4.8. 5.2 is going to be 3 little squares. That's going to be 5.2. I'm going to follow that along to the line, nice and neatly. And then I'm going to continue that now down, bouncing off my line, down to the bottom. And you can see here that it has fallen as one little square above 30. Now, here, 5 little squares is 10, so that means that each little square must be 2. So, 30 plus 1 little square will be 32. Okay. Calculate the mass of group 2 carbonate needed to produce 24 decimeters cubed of gas. Use your answer from 4.5 to help you. Now, whenever it says that, okay, that means that all I need to do is look back at that answer and start to think about how we're going to get there. Okay, so if I got told that 5.2 decimeters cubed, okay, is produced from 32 grams, okay, I need to know how much would produce 24. So if I divide both sides by 5.2, I'm going to get the number for 1. Okay, so 32 divided by 5.2. If in doubt, ask Siri. Hey Siri, what's 32 divided by 5.2?
32 divided by 5.2 is about 6.1538.
Cheers. So we've got that 1 decimeter cubed is this. So if I then times up, because I want 24, so if I now times by 24 to give us 24 decimeters cubed, okay, what does that mean? Well, I'm going to have to now times this one by 24, and that will give me the answer. Yeah, to 3 significant figures, because that's pretty standard. is 148 grams. So, we've worked that out from the previous question. So, a student heated different masses of a group 2 carbonate. The student measured the volume of gas produced. Figure 11 shows a graph of the student's results. The student calculates the gradient of the line in figure 11. The student made 2 mistakes. Okay. So, correct formula for the gradient is the increase in the volume of gas divided by the increase in the mass of group 2 metal carbonate used. The student's calculation was 4 divided by 750 equals 0.00533 centimetres cubed per gram. Well, firstly, we can see the increase in the volume of gas is 750, so it must be 750 on the top. So the first thing they've done is they have flipped the formula. Okay, they have used the formula. I'm going to use the word inversely. That actually means kind of upside down, yeah, or wrong way round numbers. The second mistake is, let's think about the increase in metal carbonate. They've said 5 minus 1 equals 4. Well, it's not. It's 4 minus 1, which equals 3 grams. So they've calculated, that's the second mistake, the mass wrong. Okay. It should be 3. So now do the calculation properly. It should be 750 divided by 3, which gives us 250 centimetres cubed per gram. A student repeated the experiment with a different group 2 metal carbonate, and it's X, we don't know what X is. The relative formula mass of X CO3 is 84, relative atomic masses are of C is 12 and O is 16. Calculate the relative atomic mass of metal X. Use the periodic table. So first thing we're going to do is we've got X CO3 is 84. So we need to know what X is on its own. So to do that, we need to know what the CO3 is. So the relative formula mass of CO3. Right, well, I've got 1 carbon and I've got 3 oxygens, because that little number, remember, only applies to the number before. I get told in the question that carbon is 12, so that's going to be 1 times 12 plus 3 times 16. 16 for oxygen. So if I add that up, that's 12 plus 48, which is 60. So if I want to know what X is, I've now got to do 84 minus 60 will tell us, because this is XCO3 and this is CO3, so that will tell us that 24 is the relative atomic mass of X. So straight away I can put that answer in. Now we can use our periodic table. First of all, we know it's in group 2, so we only need to limit our search to the second column. And if you're ever in doubt about which number is which, notice that even in the exam version there's a key. So there's no excuse, just look at the key. Relative atomic mass is the top number. So I'm looking for the top number of 24. In group 2, there it is. So therefore X must be Mg, which is magnesium. Okay. Question 5. This question is about electrolysis. A student investigates the mass of copper produced during electrolysis of copper chloride. Figure 12 shows the apparatus, and you can see there you've got a DC power supply, you've got an inert carbon electrode, so you know that that's not actually going to get involved, and you've got copper chloride. You can see here on the diagram I've got this kind of clump forming around this this electrode, and I've got some bubbles being given off at the other. What gas is being produced at the positive electron, or the anode? Okay. So we are doing electrolysis in water. So we need to think about what is about in this solution. Well, we've got copper we've got chlorine, and because it's a solution, we know we've also got hydrogen, and we've got oxygen. Okay, now let's think about what charges are on these. So copper is a positive ion, so that means that it must go to the negative electrode. Chlorine is a negative ion, so that means it must go to the positive. Now, deciding between hydrogen and oxygen is a little bit more complicated. Well, hydrogen actually tends to go around as a positive ion, so that means that it will go to, if it's going to be formed, it's going to be formed at the negative electrode. Oxygen, if it's going to be formed, is going to be formed at the positive electrode. So we've got this dual between each of them at each electrode. Is it going to be copper made or hydrogen? Is it going to be chlorine made or oxygen? At this positive electrode, chlorine is actually made. Okay, chlorine is actually made. Chlorine wins this battle. Question 2, copper is reduced at a negative electrode. What does this tell you about the reactivity of copper? Well, copper is now in the battle with hydrogen, and copper, okay, actually you can see here is made, there's no bubbles, right? So we've got to think here, how does that, we're in a duel with hydrogen, so it must be that carbon is less reactive than hydrogen. Table 4 shows the student results. By the way, if you find electrolysis hard, electrolysis I think is the hardest topic in this subject. Okay, so question 5.3, we've got this table. We've got the time in minutes here, and notice that 3 is missing. We've got to calculate the mean. It says determine the mean mass, so that means there's no calculation really necessary. It means you've got to kind of think about it and work it out. Well, if you have a look here, the mean of 1 is 0.6. Then it goes up to 1.2 for 2, 2.4 for 4, and 3.06, so roughly 3 for 5. So that means that each time you're going up by 0.6. So that suggests that here, 3, where the gap is, okay, is going to be 1.8, because if you think about it, I could just add 1 plus 2 is the 0.6 plus 1.8, which gives you that. Okay, that's horrible mathematically, by the way. Don't kill me, maths people. Calculate the mass X of copper produced in experiment 2 after 5 minutes. Okay, so we get told that 3.02 plus this number plus 3.01 gives us a mean of 3.06. So if you think about how we calculate a mean, we add up the numbers, so it's going to be 3.0. Forgotten already. Memory like a sieve. 3.02 plus x plus 3.01. And that whole thing, when you do a mean, is divided by 3, and that gives us 3.06 as our mean. So, a little bit of maths actually, let's just rearrange it, let's just work backwards. If I times everything by 3, I'm going to have 3.02 plus x plus 3.01 gives us 3.06 times 3, which is 9.18. If I then take each of them from each side, I will leave, okay, with x being 6.15. Okay, 3.15. Mr. Pashler's a moron. So if I do 9.18 minus 3.01 minus 3.02, that gives us 3.15. Okay, so that is our answer, 3.15. The copper chloride solution used in the investigation contained 300 grams per decimeter cubed of solid copper chloride dissolved in 1 decimeter cubed of water. So the students used 50 centimeters cubed of copper chloride solution in each experiment. Calculate the mass of solid copper chloride used in each experiment. Okay. So, the key thing here is to remember what a decimeter cubed and a centimeter cubed is. They're really complicated and weird units, but in your head you should think about what units you know, and that would be a litre, and a centimetre cubed is a milliliter. They're the same thing, but we always in science use decimeters cubed and centimetres cubed. That means that 1,000 centimetres cubed equals 1 decimeter cubed. Okay, so if I've got 300 grams per decimeter cubed of solid in 1, okay, so that means I've got 300 grams per 1 decimeter cubed. That means that I've actually got 300 grams per 1,000 centimeters cubed. So I can divide that and I can work out how many I've got per 1. So that would actually be 0.3 per grams per 1 centimeters cubed. What I've done there is I've divided by 1,000. But I've got told I've got 50, so that means all I'm now going to have to do is times it by 50, and that means I'm going to get 0.3 grams times 50, okay, which is 15 grams. Okay, question 6. This question is about sodium and chlorine. Figure 13 shows the position of sodium and chlorine in the periodic table. State one difference and one similarity in the electronic structure of chlorine. Well, this goes back to what we've said a lot, which is what the group numbers and what the period numbers mean. Okay, if you remember, we said that the groups are the number of outer shell electrons and the periods show the number of cells. Well, sodium and shells, so sodium and chlorine are in the same shell, so it means they have the same number of shells. Okay, and a difference is that sodium has 1, because in group 1 it's got 1 in the outer shell, and chlorine has 7. So sodium has 1 in the outer shell, whereas chlorine has 7. Sodium reacts with chlorine atoms to produce sodium chloride. Describe what happens when a sodium atom reacts with a chlorine atom. Write about electron transfer in your answer. Okay, so when you think about what is happening, so sodium is a metal and chlorine is a non-metal. And if you remember, when they react, we said this earlier on, metals, okay, lose electrons and become positive, and non-metals gain and become negative. Okay, so I can just confirm this. If I have sodium like this, it's got 1 in the outer shell. What happens is it loses that and becomes a sodium plus ion. And chlorine has got 7 in the outer shell, and it can gain that electron and become negative. Okay, so sodium loses 1 electron to form a positive ion. Okay, chlorine will gain this 1 electron to become a negative ion. Okay, nearly there. Last thing, I love it when you see in the questions. Reaction between sodium and chlorine is an exothermic reaction. Complete the reaction profile. So, if you remember reaction profiles, and if you remember, we said earlier that that exothermic means exit energy. So that means that this energy in my reactants locked away has got to be released. If you think about it like that, right? This is my money in my bank account. If I give out money, the money left in my bank account is going to go down. Okay, so if I go, oh, I want to buy a PS5, yeah, I get really happy and I give out lots of happiness, but my level goes down. So my products must be lower. Okay. Now, to complete the reaction profile, we need to think about what happens in the meantime. Well, to have a chemical reaction, we need to first break the bonds of what's in there originally. So I have to put in some energy to break the bonds. And this kind of increase in energy at the start is called the activation energy. So all of these reaction profiles have this initial hump, and then you've got to decide, does it end up lower or does it end up higher? But because it's an exothermic reaction, we get this. A student plans a method to prepare pure crystals of copper sulfate. A student's method is add 1 spatula of calcium carbonate to dilute hydrochloric acid in a beaker. When the fizzing stops, the heat solution with a Bunsen burner until all the liquid is gone. This method contains several errors and does not produce copper sulfate crystals. Explain the improvements the student should make to the method so that the pure crystals are produced. The easiest way to explain, okay, the mistakes is to go through the method yourself and then correct them. Okay, so the first thing to do is realise you're making copper sulfate, and they have chose to use hydrochloric acid. Okay, so mistake number 1, okay, is the student should use sulfuric acid, as this will make a sulfate instead. Oh, I've got to use the F, haven't I? I'm going to leave it as the pH. Old habits die hard. As this will make a sulfate instead of the hydrochloric acid, which makes chlorides. So straight away I've explained the issue that they've got. Okay. Now they've also decided to use calcium carbonate. Well, I'm after copper sulfate, so they should also use copper carbonate instead. Okay. Now here's the first thing. Whenever I am adding the base to the acid, the important thing is that I make sure all that acid is reacted. So the student, so this is my next mistake, because they had it as 1, is should add the carbonate until no more reacts. Okay, what I mean by that is it is in excess. Should be 2 different words. Okay, once I've got that, I've now got that solid lying about, so I have to get rid of it. Okay, so they should then filter this to remove excess solid. And now I've got that, instead of heating until all the liquid is gone, okay, they should finally heat gently. Okay, you can even do this over like a water bath or something, until nearly evaporated, and left to slowly crystallize. Okay, that's not an easy paper, and I hope that you found that useful. I know I like to waffle and rabbit on, and you might think, feel scared by the length of the video, but I hope you appreciate that as I'm going through, I'm trying to explain the science behind it, not just kind of blindly doing the exam. But that is the Combined Science Trilogy 2018 Chemistry Paper 1 Foundation Tier. Until next time.